All right, let's crack the code. Today, we're diving into the invisible forces that pretty much shape our entire world, chemical reactions. I'm talking about everything from the sizzle of a steak on a grill to the very air you're breathing. Chemistry is happening all around us, all the time, and we're going to figure out how it all works. So let's just jump right in with a little bit of a puzzle. Picture this. You take a simple white powder, in this case lead nitrate, and you start to heat it up. All of a sudden, poof, this cloud of brown fumes appears. It's a really dramatic change, right? But the question is, what is actually happening on a molecular level? To solve a puzzle like that, we first need to learn the language. We have to understand how chemists describe these incredible transformations that are going on. Well, we do it with something called a chemical equation. Honestly, the best way to think about it is like a recipe. It tells you the exact ingredients, which we call reactants, and what you end up with at the end, the final dish, which we call the products. Okay, but before we can even start writing our recipe, we have to know the single most important rule in the entire chemical kitchen, and that is the law of balance. You see, a lot of the time we start with what's called a skeletal equation. It looks something like this. Mg plus O gives us MgO. It gives you the basics, right? It lists the ingredients, magnesium and oxygen, and the product, magnesium oxide. But it's kind of like a recipe that just says use flour and eggs to make a cake. It's missing the crucial amounts. It's just not balanced. And here you can see the difference, plain as day. On the left, you've got that unbalanced skeletal equation. But on the right, you have the fully balanced version. Now notice a couple of things changed. We've got these big numbers in front now. We call those coefficients. And you'll see oxygen is written as O2. Why? Because oxygen gas, the stuff in the air, just naturally hangs out in pairs. This balanced recipe now has the perfect proportions, which means nothing is being created out of thin air. And the reason we do all this, the reason we're so obsessed with balancing, comes down to this fundamental law of the universe, the law of conservation of mass. It just means that matter can't be created or destroyed. So in a chemical reaction, atoms are never lost or goined. They're just rearranged. That's why the number of each type of atom has to be exactly the same on both sides of that arrow. All right, so with that golden rule in our back pocket, let's look at two of the most basic types of reactions you'll ever see. Building things up and, you guessed it, breaking them down. First up, we've got combination reactions. And they're pretty much exactly what they sound like. Two or more simple things combined to form one single more complex thing. A really classic example is when you add water to quicklime, you get something called slaked lime. And this reaction, it also happens to release a ton of heat. You can literally feel it getting warm. And on the flip side, you have decomposition. This is where a single compound breaks down into simpler parts. But here's the catch. It usually needs a little nudge of energy to get going. What you're seeing here is a process called electrolysis, where we're using electricity to split water back into its core elements. Now, the balanced equation for splitting water tells the whole story. It shows that two molecules of liquid water will break down to form two molecules of hydrogen gas and one molecule of oxygen gas. See? It's a very specific recipe. It's not just a simple one-for-one split. And because of that specific recipe in our equation, we get this result every single time, a perfect 2-to-1 ratio. You will always produce exactly twice as much hydrogen gas as you do oxygen gas. It's a perfect, visible demonstration of that whole law of conservation of mass thing we were just talking about. Okay, next up, let's get into some more dynamic reactions. The ones where atoms don't just join up or break apart. Instead, they decide to swap partners. So first, you've got a single displacement reaction. This is where a more reactive element literally kicks a less reactive one out of its compound. It's like a chemical cutting in on the dance floor. For reasons that are a whole other story, zinc is just more reactive than copper. So when you drop a piece of solid zinc into a copper sulfate solution, the zinc shoves the copper out of the way and takes its place. And then you've got double displacement. And if single displacement was one dancer cutting in, this is like two couples on the dance floor just deciding to swap partners. You mix two solutions, like barium chloride and sodium sulfate, and all the positive and negative ions trade places. And when they do that, they often form a brand new solid substance that can't stay dissolved. We call it a precipitate, which then falls right out of the solution. So you can see that reactions aren't just about atoms shuffling around, they're also about the flow of energy and this invisible trade of tiny particles called electrons. Right, so some reactions are exothermic. They release energy, usually as heat, which makes everything around them feel warmer. Think about burning natural gas in your furnace. Others are endothermic, meaning they have to absorb energy from their surroundings to even happen. You know those instant cold packs you snap to activate? That's an endothermic reaction in action, pulling heat away from you and making it feel cold. And finally, you've got redox reactions. And these are all about the transfer of electrons. It's pretty simple. When a substance loses electrons, we say it's oxidized. When another substance gains those electrons, we say it's reduced. So in this example, which is how we make iron from iron ore, the carbon monoxide gets oxidized, while the iron ore gets reduced. Okay, so why does any of this actually matter? Well, because these reactions aren't just happening in some far-off lab. They're happening everywhere, all the time, from huge industrial factories all the way down to the individual cells inside your own body. I mean, look at this. That incredibly intense thermite reaction that welds railway tracks together, the decomposition reaction that made old-school black and white photography possible, and yeah, even the simple act of breathing, that's a combustion reaction that's powering your cells as we speak. All of these different types of chemistry are literally the engine of our world. So when you get right down to it, a chemical equation is so much more than just a bunch of symbols and numbers. It's a tiny, elegant story about change. Each one is like a short poem, written in the universal language of chemistry, and it describes a fundamental transformation of matter. And that kind of leaves us with one last thing to think about. We mentioned respiration just a second ago. That's a mind-bogglingly complex series of chemical reactions happening in trillions of your cells right this very second. So what other incredible transformations are you a part of right now without even realizing it?